Hi, hello. Very good evening to all students. Okay, welcome to tonight's webinar. I'm a teacher James, and together with me, I have a teacher Quilin. So tonight, both of us will be here to actually go through with you, okay, this topic on differentiation. Now, I know this is now getting very close, okay, to your paper, and I hope those of you who have some of the paper already taken, okay, I hope you have been doing well so far. All right. So for tonight, differentiation. Now, this is an important topic in AMAT, okay, under the topic of calculus. Now, it's an important topic not only by itself, okay, as in there'll be question on differentiation. So you need to know the technique of differentiation very well and to be able to apply into different contexts. But it's also a very important topic because it will help you in another topic, right, which is integration. So for those of you who want to do well in integration, you must be very strong in your differentiation, okay, because it will help you. Right, so that's why for tonight, we have actually prepared this topic on differentiation. And what we have done is that, I mean, by now, I believe many of you should have already learned this topic, well. But in case if there's any aspect of it that you are still not very familiar, I hope this session is to really help you, as a last minute recap on some of the key concepts, as well as especially the one on the technique of differentiation. So what we have specially prepared for you all tonight, okay, is we'll be going through with you the different rules of differentiation, okay, to help you to do a recap. And not only that, in differentiation, typically there will be application question. So we have also actually prepared the different types of application questions that you can expect to get. Okay, these are the trending type, whereby typically this will be those different type of applications that will be actually that you have a good chance of seeing them. Okay, now the question can change. The context of the question can change. But what we want to focus on tonight is really in terms of the method. Okay, and to also understand why are we doing certain steps. Okay, so tonight I will be focusing more on the technique as well as the method, okay, and to let you understand and properly appreciate why you're doing certain steps. Okay, and we will also be highlighting to you as we go through the step some of the points to take note and some of the common error that student might make. All right. Okay, so this is what we will focus on tonight, and please feel free to actually interact with us. If let's say you have any question or anything that you would like to understand a bit more, okay, on this topic. Okay. All right. Maybe just have a quick check in with everyone. Is there anyone that is not from Sec 4? That means not doing your Sec 4 this year. Any Sec 3 student? Okay. Okay, can. I see a very small number. Okay, but very good. Okay. Thanks for taking the initiative. Even though we're in Sec 3, but you have actually joined us for this seminar. But I can see that the vast majority, of you are actually O-level students. All right. So okay, good. So tonight we will start off with differentiation, and I will let teacher Quilin to start off with the first part. Okay, and then later on I will take over from there. All right. So teacher Quilin, I pass over the screen to you.
Oh, hi. Okay, thank you, teacher James. Okay, so let me share my screen first. Oops. Okay, where was this? Okay, sorry, I was actually scrolling down to another page to take a look. All right, so let's get started. So for today, this is the first part which we will be going through. Okay, fundamentally, we need to know all the different rules and the way to actually to differentiate when we do differentiation. How do we actually solve it and so on. So these are some of the basics that we need to be very familiar with before we actually head on to the questions itself, right? So you would have actually got this in your worksheet as well. So let's take a look, run through on this. And maybe I'll also for certain rules or certain things that you see here, we will actually also have a simple example that I will show you as well. Okay, so first of all is that when we talk about differentiation of a constant, where a is a constant, right? For this first one, so this one for sure is that when we differentiate a constant, that will be equals to 0, right? So this one should be rather straightforward. Okay, then for the next one, differentiation of this x to the power of n, right? So what happens is that this will then become n times x to the power of n minus 1. Okay, so for some of you, if let's say not the so conventional kind of method is that you would always you can actually think of it that way, is that if I want to do a d dx of x to the power of n, this also means that what is this? Sorry, let me rewrite this a bit. So it is actually like as if like you have your x, then your n, what you do is you actually trying to bring this down to the front, okay? And then, but on top of that is that this, you will have to actually put a n minus 1 over here, right? So this is actually a not so conventional way, but I think this actually helps in terms of the visual, for some of you who are more visual and you need to actually have this to get you to be more familiar, right? And also for that few of you who are Set 3, so this is actually going to come in very soon. So just to have a brief idea of this as well. Okay, so so that means what I mean by this that means it's like if let's say I have x d dx. Sorry, let me change the color again. Okay, so for example, if it's d dx of a very simple one, x squared. So what happens is this will actually become 2x and then followed by 2 minus 1. The index of 2, now we minus 1. That means it will be just left with 1, right? So of course, we don't have to write the 1. So then that will be left with 2x. Or if let's say we were to consider x cubed instead, okay? If it's x cubed, then it will be just 3x, then 3 minus 1, it will be 2, right? So that's more or less what you should know, right? Then, and the next one is that you have this a ddx of ax to the power of n. So the a is a constant, right? But it's actually multiplied to this x to the power of n. So this multiple will just stay there. And what happens is the differentiation actually involves with the x to the power of n, where this becomes n times x to the power of n minus 1. So because we earlier on we have this a here, so that's why it will be a times n times x to the power of n minus 1. Right, so that's why you have this as written as anx to the power of n minus 1. Okay, all right. As you before I go into the fifth one, which you notice I've already written this word here. Later we'll talk about that. All right, so this next one is if let's say we have a case of having two functions. Let's say like first function is maybe x squared plus 1. Then the other one is maybe plus 3x square, sorry, 3x, no, sorry, maybe 2x cubed, or maybe even it's not even a x cubed, just so simple. It could be like maybe e to the power of x. Then how would you actually do this? Then that means when we do a differentiation, then we will have to, it is just simply differentiate the first one and then plus the differentiation of the second term that you see there, right? Or the second function that you see there. So then eventually you just have to add the both the two derivatives where it becomes this final answer here, where you see over here, right? So that is more or less what you should have already covered. I mean, you should have already learned in school as well. So it's just a quick recap of it. Okay, then the next one. This is the one which why I actually write if you can recall, this is actually what we call a chain rule, right? So if let's say I have a function that is to the power of n, for example, let's say I have d dx of, let's say I have x cubed plus x square, a very simple one, all right? Then after that, I have a square here, right? So what happens here? Then I will have to actually, first of all, where you see here is n times of the function to the power of n minus 1, then multiplied by the derivative of the function, right? So that means this is actually going to come out as 2 times x to the power, no, wait, let me rewrite this a bit so that it is actually more visible for you to see, right? So let's say maybe I have this as x cubed instead, okay? Sorry about that. Okay, so that means what we will have is 3x cubed plus x square, right? Then this actually becomes square here, right? And then after that, plus, sorry, not plus, it's a times, okay? It's a multiplier. I actually write wrongly. So this is actually multiplied by the whatever that is inside, okay? You differentiate whatever that's inside, which is 3x squared plus 2x, okay? And then, of course, you have to go further to the final step eventually, right? So to simplify this, right? So this is more or less a basic, just an introduction to those who haven't learned it yet, and those that, yeah, it's just a recap for you, right? Okay, then the next one that we have here is actually the dx of uv. Okay, so in the case that if let's say we have two functions as well, right? Like for example, it's a bit similar to this fx and gx, but instead of putting it as fx and gx, we actually put it as u and v. We substitute the function as u and v so that we can actually differentiate in such a way where it's u multiplied by dv dx plus v multiplied by du dx. Okay, so this is actually also what we call the product rule. And then after that, the next one is the quotient rule, where it's actually when you have a function over another function, right? And this is actually v du dx minus u dv dx over v squared. Okay, so this is the quotient rule. Okay, so this one we will actually look at it in more details later when we are actually applying the question itself. And also, it's actually in the questions itself where we will actually look at it in more details, right? Okay, so moving on, this next one that we have here, this is actually a differentiation of exponential functions. So when we are doing a differentiation of this e to the power of x, it is just simply e to the power of x. Okay, there's no change in this, right? Whereas for a case of differentiation of e to the power of ax plus b, that is when we will have to consider putting the e to the power of ax plus b, but we have to differentiate on top of that. It is also considered a chain rule where we will have to differentiate the ax plus b, this portion here, right? So when we actually differentiate this ax plus b, it's only just a that is the derivative. So that's why it will become a times e to the power of ax plus b, right? So, and if it's a case of a function that you see that is e to the power of a certain function, maybe it's more complicated kind of variables, right? So then that will actually come out to be the derivative of the function times e to the power of the function, right? Okay. Next is actually the logarithm functions. Okay, differentiation of logarithm functions. So if we were to have a case of differentiating ln x, So ln x, what will happen is that this will become 1 over x. Okay. And for the differentiation of ln of a function, okay, fx, this will then be, okay, same thing is that it will be actually a case of, if we were to rewrite this more clearly, is that we are actually doing a differentiation of the fx, the function. So that will actually give me the derivative of the function, right? And then I am actually multiplying by the 1 over fx. Okay, so of course, at the end, this actually becomes just the derivative over the function. Okay, right? So then the next one is the case of differentiation of a function multiplied by another function. So what we can do for this is that we can actually separate it out. Okay, because remember your logarithm, the laws of logarithm. Okay, when let's say I have ln of for example, maybe just a very simple one, a times b, right? And this is actually what we can also rewrite it as ln a plus ln b, correct? So for this situation is that if we were to do a differentiation of a ln of a function fx multiplied by another function gx, we can actually separate it into the differentiation of ln fx plus ln gx. And that the next thing is that we can actually look back into this earlier part where how we actually do this is actually a case of just something like this, the differentiation of a fx plus or minus of a differentiation of a function fx plus or minus a function of gx. Okay, so and also another thing is that then we can also follow back to this previous rule that we see here, right? Which is when we have a ln of a function, then it will be just a derivative of the function over the function. Okay, so and next one is this ln fx over gx. Okay, same thing is that we will have to consider this law of the logarithms where if it's a ln a over b, logarithm of a over b, this is also ln a minus ln b, right? Okay, so with this, that is why you have this to be simplified. Not say simplified, we actually separate it out, right? To be d dx of ln fx minus ln gx. And then same thing goes again where we can actually separately differentiate them. Okay. All right. Then moving on the next page. This one will take a bit more time to talk about it. Right. So if you were to look at this, is that this differentiation of trigonometric functions is to some students, this may be a bit of a headache. Okay. Right. But okay. One thing is that for certain rules, there is no choice where you have to try and memorize it. But of course, if you are very familiar with it already, once you actually do enough practice, you will realize that it just comes to you very naturally, right? So, but of course, if you are still not really so familiar with it yet, then probably you may have to try to memorize some of these rules. Okay, so like for example, the differentiation of your sine x, this will then be equals to cosine x. Okay, differentiation of cosine x. Okay, remember this cosine x, when you differentiate cosine x, it is a minus sine x. Okay, there is a negative sine x. There is a negative sign in front. Don't forget about it. Okay, you may think that, oh, sine x, the differentiation sine x, so it should be the opposite, that is cosine x. But for cosine x is not, is that there will be a negative sign that is in front, right? So you can also think of it in the sense that, okay, maybe I don't complicate things with the quadrants, because then I will have to actually try to prove it to you at this point, right? So but anyway, so just remember, okay? Then next one is that if we were to have d dx of tangent x, okay, so for tangent x is that it will actually give you secant square x, okay? And this, there is actually a reason for this, because if you were to think of it, think about it, tangent x is also what? It is also, let me change the color first. Okay, so tangent x is actually sine x over cosine x, right? And if we were to do a d dx of this, okay, so what happens? Then we will have to remember, we have to actually use the quotient rule already, right? And then using the quotient rule, that means this is going to be what? It is going to be b du minus ud, wait, udv minus vd. Okay, sorry, I actually kind of got it confused. Okay, it's vdu minus udv. Okay, so that means it's going to be cosine x. Then after that, differentiation of your sine x is cosine x, right? And then your minus your sine x u dv. So that means it will be multiplied by a negative sine x. And then over v square. V square, that means it's cosine square. Okay, so which means to say that this is going to give me cosine square x plus sine square x over cosine square x. And what is cosine square x plus sine square x? That would be 1, right? Equals to 1. So that means I will be left with, I'll be in the end, I will have 1 over cosine square x, which then that is actually 1 over cosine. 1 over cosine is actually secant. So that means this is going to be secant square x. Right, so this is actually, if you happen to be asked to prove, so this is actually how you can prove it also, right? Okay. Okay, so moving on, if let's say I have a case of d dx kx, d dx of your k sine x. Okay, so the k, we can think of it that is the constant. We can consider this as a constant. So that means k sine x, then it will just simply be the differentiation of the sine x to be cosine x. And the k is just a multiple of it, right? And then for differentiation of k cosine x, then remember, because your cosine x is equals to differentiation of cosine x is negative sine x. So that's why you have negative k sine x. And of course, for the differentiation of k tangent x, that will be k secant square x. Okay, all right. Then the next one, the next group that you see here, this is actually if there is a case of not just a simple x as the angle. If this is going to be sine x, sine ax plus b, right? And differentiation of this, what will happen? Then we got to consider back the chain rule again, which is this sine, we will have to differentiate it as to change to cosine, but keep whatever that's inside the same, right? Then after that, we differentiate the whatever that's inside here, which will give me ax, differentiate of ax plus b, I will get a only, right? Okay, and then similarly for cosine, differentiation of cosine ax plus b, then that will be equals to negative sine ax plus b, and the next is d dx of tangent ax plus b. That will give me a secant square ax plus b. Okay, and following that, okay, so this is actually going to be a slightly tougher kind of chain rule, that if we were to consider a case of sine to the power of n, and then ax plus b, then of course same thing, chain rule, where we will have an sine n minus 1 to the power of n minus 1, then times ax plus b multiplied by the cosine ax plus b. Okay, so similarly, that also goes for the other two, which is the cosine to the power of n ax plus b, and also for this differentiation of the tangent to the power of n of ax plus b. Okay, right? Okay, so yes, I have talked a lot about this one already. So I think I will go into this next part, which is the first question. Okay, so let's do some practice here. And okay, so this question here, a curve has the equation y equals to ln secant square x plus cosecant square x for 0 less than x less than pi over 2. Okay, and you are to prove that secant square x plus cosecant square x equals to 1 over secant x cosine x whole thing square, right? So first of all is that you notice this is actually given to you, but and you are to actually do this. So this is actually proving which is actually in your trigonometry, right? So there are times where they will actually combine certain concepts and ask you at the same time. So you got to be very familiar with all these that you have learned previously as well, and then try and solve accordingly to what they ask you. And after that, you notice there is this word here, which is hence, which means you need to actually use what you have found in the earlier part, which is basically this proving. And using this, we will have to solve to show that this dy dx is equals to -4 cotangent 2x. Okay, so part A. Part A, for this, we can consider doing it from the left-hand side because this looks more complicated as compared to the right-hand side. So we will usually do work the question for proving of trigonometry equation. We will usually prove it from the side that is actually more complicated, right? So secant square x plus cosecant square x. So, excuse me for that. Let me rewrite this. Okay. Okay, so this is left-hand side. Secant square x plus cosecant square x. Okay. This is also 1 over cosine square x plus 1 over sine square x. Okay, so after you change it to 1 over cosine square x and plus 1 over sine square x, then we can actually bring these two fractions together. Okay, so bringing these two fractions together, this means that this is going to be cosine square x. No, wait, let me rewrite this. Okay, so this should be sine square x plus cosine square x, okay, over. Actually, there's no difference whether I write the cosine square or sine square first, but I try to present it in the more appropriate way because you are seeing that it's kind of like a cross multiply, right? Your sine square goes over to your fraction of 1 over cosine square, right? So then this denominator will actually be, if we were to multiply these two together, this is actually sine square x cosine square x, right? Then from here, this sine square x plus cosine square x, remember I mentioned earlier before, is that this is actually equals to 1, right? So then we can actually just put this as 1 over sine square x cosine square x. Okay, and we can actually take out the square from the sine and sine x and cosine x, so that it can actually be like what you see over here, right? So then this will then be equals to sine x cosine x, opening bracket, square, right? Okay, so then that is also equals to your RHS, right hand side. Okay, shown, proven. Okay. All right, then for part B, hence show that dy dx is equals to -4 cotangent 2x. -4 cotangent 2x. Okay, so before we actually do this, we will have to consider what we have here. This y equals to ln secant square x plus cosecant square x, right? We can actually, based on what we have just proven for part A, we will substitute this into this equation, right? So that it is actually more convenient for us to work on this question, this part B, right? Okay, so first of all, y is equals to ln secant square x plus cosecant square x. This is also equals to your ln 1 over sine x cosine x whole thing square, right? Okay. Right, then after that, next, with this, remember it is actually a 1 over a denominator. So for this kind of situation, we can actually, and it's actually ln, no, sorry. So this is actually, we can rewrite this as 2 ln sine x cosine x. Sorry, negative, because it's a power of 2, -2, okay? Yeah, so this is actually 1 over this whole thing square, right? So it is actually also a power of -2, sine x cosine x to the power of -2. So when we can actually rewrite it as -2 ln sine x cosine x. So then we will have the final part, which is -2 ln bracket ln sine x wait, okay, I think I better write it with the bracket. It will be clearer for you to see as well. Okay, so then ln bracket cosine x. Okay, so this will be the what you need to write first. Then from here, then we can actually work on the differentiation. So dy dx will then be, okay, let me shift this a bit. Okay, -2 okay, so for this ln sine x, differentiation of ln sine x will give me cosine x over sine x plus ln of cosine x will be sine x, sorry, minus. Okay, so this is actually minus because cosine is actually going to be a negative sine x, right? So then minus sine x over cosine x. Okay, then we can actually simplify, we can bring the fractions together. This will be sine x cosine x for the denominator, while the numerator will be cosine x, cosine square x minus sine square x. Okay, so for this cosine square x minus sine square x, if you can recall, this is also cosine 2x. Okay, so which then we can actually change this to cosine 2x over your sine x cosine x. Remember, okay, let me maybe just write it at the side so that you can actually have some reference. So if let's say I have cosine 2x, this we can actually re-express it as cosine square x minus sine square x, right? And for this sine x cosine x, we can think of this as sine 2x. Think of sine 2x first. Okay, think of sine 2x and what is it going to give you? It's actually going to give you 2 sine x cosine x, right? But however, we only have sine x cosine x, which means to say that it is just half of it. Half of what you have for sine 2x. So then that means this we can actually rewrite as half sine 2x. Okay, and this half over here, that means it's actually going to become a 2. So 2 times -2, that would be -4, right? And sine 2x over, cosine 2x over sine 2x, that will give me what? It is actually also your cotangent x, right? Okay, let me shift out slightly bit more. So this is going to be cotangent 2x. Okay, so that is actually what you are supposed to show. So therefore, shown, right? Okay, I'll hold on for a short while. Let's just take a look if there's anyone has any question. Okay. Yeah, so as I was actually trying to say that, yeah, this one we actually got to use the double angle rule to subsequently solve this part. Yeah, right. So okay, let me just maybe scroll back slightly bit in case if anyone missed out anything. All right, so this is the first part A. Okay, and then followed by part B. Okay, if you need to, you can also take a snapshot of this. But of course, we will be sharing the video. Will we? Teacher James, just to check, we will be sharing the video as well, right? With the group, right?
Yes. So this will be
Okay.
recorded, and then at the end of the session, we will do that.
Yeah. Okay. Yeah. Thank you. All right. So yeah. So if you have missed out anything, you can also look at the videos as well. Okay. So So let's move on to the next question. Okay. So this next question here is a question on exponential, right? So given that y equals to e to the power of 3x multiplied by 1 plus x, you are to prove that the second derivative, which is this d2y over dx squared plus 9y is equals to 6 times of the dy dx, right? So first of all is that we can actually solve, we can try to differentiate this first. So for y is equals to e to the power of 3x times 1 plus x. Okay, we can do the dy dx first. This will then be e 3x. Okay, so this is your u dv plus v du, right? And it will just be e to the power of 3x multiplied by 1 because differentiate of x is just 1, right? And then plus 1 plus x. Differentiate your this e to the power of 3x will be 3 times e to the power of 3x. Okay, so then simplify this. Of course, you can factorize out the e to the power of 3x first. This will then be e to the power of 3x multiplied by, okay, so you have the 3, no, you have the 3 plus, wait. Okay, maybe I rewrite this, another extra step so that it's actually clearer for all of you to see. Okay, so this is going to give me e to the power of 3x plus e to the 3e to the power of 3x plus x times 3x e to the power of 3x, right? So this is actually what, if you were to do an expansion of it, but you will notice that the e to the power of 3x is a common factor, right? So then that will be e to the power of 3x bracket 1 plus 3 plus 3x. Okay, all right. So then this will then be e to the power of 3x bracket 3x plus 4. Okay, right. Then moving on, the next thing to do is to find your second derivative. Okay, second derivative is, okay, let me just write this again. d2y over dx squared. This will then be e to the power of 3x multiplied by 3, because differentiate of 3x plus 4 is going to be 3, then plus, this case will be 3x plus 4 multiplied by 3 to the power 3 times e to the power of 3x. Okay, so if we were to consider this is going to give me same thing, we can factorize out the e to the power of 3x first. Okay, so this time around I won't actually expand it out first. So I will just straight away factorize, and what I will get is actually going to be 3 plus 9 times 3 times 3x times 3. Okay, so be careful of this. 3 times 3x will be 9x, then plus 4 times 3. 4 times 3 will then be 12. Okay, so then this will then give me e to the power of 3x times 9x plus 15. Okay, of course, you may say that, should I actually factorize out the 3 also? It's okay that you don't have to actually do that, because we can just keep it here. Then we just move on to the subsequent part, which is to find this d2y over dx squared plus 9y. Okay, so with the two values that you have gotten, okay, so d2y over dx squared plus 9y, that will be, okay, so substitute this d2y over dx squared. This is actually e to the power of 3x 9x plus 15, and then plus, okay, what was your y? It was actually e to the power of 3x multiplied by 1 plus x. Okay, so, and this is 9 times of it, 9 times 9y. So 9 times of it. Then over here, we can, same thing is that we can actually factorize out the e to the power of 3x. Okay, and this will then be 9x plus 15. Okay, so 9 times 1, 9 times x. So remember that, I should have actually draw the bracket so fast. Okay, so this is going to be plus 9 plus 9x. Okay, right. So then the next step is you will then get e to the power of 3x multiplied by 18x plus 24. Okay, then at this point, then that's when you have to factorize out, because we are trying to prove that it is actually 6 times of the dy dx, right? So we can actually factorize out the a 6 from this. So this is actually 6e to the power of 3x multiplied by 3x plus 4. And you notice that this e to the power of 3x times 3x plus 4 was your dy dx, right? So then this will be equals to 6 dy dx. Okay, so there you have it. It is proven. Okay. Okay, maybe I just shift back up here first, just in case if anyone missed out anything earlier, right? Then I'll slowly scroll down. Okay, then moving to the next part. Okay, now let's go on to the next question. Question 3. Okay, so question 3 is that there is this partial fractions, and you are to express this fraction as a partial fraction. So we can see that this we can use a long division method, and it is actually rather straightforward, where we see that this is just plus 3x plus 4, right? So that means part A, we can say that it's using long division method, long division. This x square, okay, let me rewrite this, which is, let's say I were to actually write this out, it is actually your x square plus 3x plus 4, and this one is x square minus 5x plus 6, right? So what you will have here is actually just 1, right? And what is it? It is actually x squared minus 5x plus 6. Okay, so there's a minus of this. So end up, this will be just left with, okay, so this will be plus, so this will be 8x minus 6, so this is 8x minus 2, right? So then that's that means your x squared plus 3x plus 4 over x squared minus 5x plus 6 is equals to 1 plus 8x plus minus 2 over x squared minus 5x plus 6. Okay, and you will see that this actually we could have factorized this, okay? But just to consider for this division, to take out this one whole first, I didn't actually do a factorization so early, right? So over here, then we can actually rewrite this as, okay, so x squared minus 5x plus 6 is actually just going to be x minus 2, x minus 3, right? Okay, so then of course your numerator is at 8x minus 2. Okay, so after this, we can actually further work on the partial fractions, where you have your, let this 8x minus 2 over x minus 2, x minus 3 to be equals to a over x minus 2 plus b over x minus 3. Okay, so then that would then we can actually cross multiply. Sorry, not cross multiply, as in we multiply the throughout by x minus 2, x minus 3. We will have 8x minus 2, where this is a times x minus 3 plus b times x minus 2. Okay, then that will then be, okay, wait, we have to actually consider when x equals to 3. And we will have 8 times 3 minus 2, 8 equals to, A will be 0 already, right? So then your B is 3 minus 2. So this means that your B, eventually it will become B equals to 22. And when your X is equals to 2, then that will be 8 times 2 minus 2 equals to A times 2 minus 3. And then that means your A is going to be, let me shift up slightly. Okay, so this is A will then be negative 14. Okay, so that means your final answer for this, for the partial fractions, x squared plus 3x plus 4 over x squared minus 5x plus 6 is going to give me 1 minus 14 x over 14 over x minus 2 plus 22 over x minus 3. Okay, so there you have it. So this is actually for part A, right? Then we got to move on to part B. Part B is actually quite a simple one where we have to find the gradient of the curve where at x equals to 1, right? So to find the gradient at x equals to 1, first of all, we find what is dy dx first. Your dy dx, okay, so wait, maybe I rewrite this again, so it's actually much clearer for everyone to see. So this is actually your y is actually, what we have was this x squared plus 3x plus 4 over x squared minus 5x plus 6, right? So this can also be rewritten as y equals to 1 minus 14 x minus 2 over x minus 2 plus 22 over x minus 3. Okay, then your dy dx, this will be just 14 over x minus 2 square minus 22 over x minus 3 square. Okay, then at x equals to 1, we just have to substitute this value into the dy dx, where your gradient then becomes 14 over 1 minus 2 square minus 22 over 1 minus 3 square. Okay, and you will eventually get 8.5. Okay, as your final answer. Right? Okay, just scroll back a bit just to ensure that everyone has gotten this. Okay, so this is the first part, part A. And then part B. Okay, let's move on. Okay. Okay, so this next question here, you have this increasing, before we go to the next question, is actually this part, which is talking about increasing and decreasing function. All right, so this diagram, as you can see, it shows a curve of y equals to fx, where your y values increases as the x values increase. So when that happens, when both are increasing at this, in this case, then that is when we consider this as an increasing function. So, which means your dy dx is greater than 0, or we can say that dy dx is a positive value, right? And if the case of this y equals to gx, this is a bit different, where y value decreases as the x value increases. As you increase in your x value, but y actually decreases. So this would then be a decreasing function where your dy dx will be less than 0. Okay, so we have a question for this, where this equation of a curve is given by y equals to ln x over 5x. So find the values of x for which y is a decreasing function. Okay, so let's do the dy dx first. So dy dx is actually, how do we do this? Is using your quotient rule, right? So this will be 5x multiplied by 1 over x minus ln x multiplied by 5 over, so is v squared. V squared will be 5x squared. Okay, then that will give me 5 minus 5 ln x over 5x squared will then be 25x squared, right? And then we notice that this 5 is a common factor on the numerator and the denominator, right? So we can actually divide both by 5, and this will be simplified to 1 minus ln x over 5x squared. Okay, so and it says that find the values of for which of x for which y is a decreasing function. So y is a decreasing function, which means to say that your dy dx has to be less than 0, right? So which then means that we can actually write this 1 minus ln x over 5x squared less than 0. And since we can say that when we look at this, how do we actually go on to solve it? Is that you will notice that this 5x squared, whenever there's a x squared, whenever something is being squared, it is going to be always going to be positive value, right? So we can actually say that since, oops, let me rewrite this a bit. Since 5x squared is greater than 0, we can actually just consider the numerator, which is 1 minus ln x less than 0. Okay, and we can rearrange this to be negative ln x less than negative 1. Okay, and if we were to change this, multiply negative throughout, then this will be ln x greater than 1. Okay, so there's a change of sign, in the inequality sign. So then that will be x is greater than e. Okay, e to the power of 1. Okay, so that is all for this question. Okay, let me just shift out back again, just in case if you missed out anything earlier. All right, then, yeah, so that is all for this question. All right, so the next part is actually on equations of tangent and normal. Okay, so I'll pass on over to Teacher James to actually to continue. Yeah. Okay.
Okay, yeah, thank you, Teacher Quilin. Okay, so what we have gone through just now was the first of in terms of application of differentiation, right? So just now you have seen that after going through the different techniques of the differentiation, one of application is involving what we mentioned just now about increasing and decreasing functions. Now I'm going to go through the next part, which is another very popular type of question involving application in terms of finding tangent and normal. Okay, so let me pull up my screen on this. Okay, you can see my screen, huh? Okay, now as we see just now, dy dx represent the gradient. So we've seen just now about the increasing gradient and increasing function and decreasing function, right? Whereby the gradient is always positive or whether the gradient is always negative. Now, always remember dy dx represent gradient, okay? And when we talk about that, the expression that we carry out after we differentiate, we get dy dx. The expression represents the general expression for gradient. Meaning to say, at any point, okay, we can find the gradient of any point, okay, because the expression of dy dx represents that. As we do the operation, always like to highlight to students that you must always understand exactly what is the significance or what is the meaning of that particular step they are doing. Okay, because I have also encountered students who doesn't really appreciate. Okay, they don't remember the step. Okay, they always know that okay, dy dx. Okay, I know how to differentiate, so I get my dy dx. Okay, but exactly the subsequent step, how to do it, and why you want to do that, they can't remember the step and they just do it. Okay, without proper appreciation. So later on, when we go to the other topic on rate of change, okay, I will highlight some of the aspects to you as well. Okay, so in terms of finding equation involving tangent, so once we know the dy dx expression, you can find the tangent, the gradient of tangent at any point. Okay, because usually they will give you information with regard to which particular point they want you to find. Okay, in terms of the gradient of the tangent. Okay, so given the fact that now we understand that dy represent the general expression for gradient at any point, we just simply need to substitute that point into the expression of dy dx, and you will know the gradient of the tangent. Okay, and then you will be able to find the equation of the tangent. Okay, because so long as you have one known coordinate and the gradient, you will be able to find the equation of a straight line. Okay. Now, similarly, if they were to ask you in terms of normal, then just remember what you learned in coordinate geometry, right? So if you know the gradient of tangent, normal will be just simply -1 over the gradient of your tangent. Okay, so so if you can do that, actually you'll be able to solve equation involving normal as well. Now the next question that I prepared for everyone tonight, okay, to demonstrate how we can actually apply this aspect of differentiation. Okay, so let's take a look at this question here. Okay, so you are given a curve y equal to cosine 2x minus 3 sine x, okay? And the normal to this curve, okay, at a point where the curve crosses the y-axis, and it actually passes through this point, okay? This point, P, comma 7, okay? So we're asked to find the value of P. Now you will see that there are many different variations to a question involving tangent and normal. Not necessarily they will just simply ask you for the tangent or the normal. The question can be actually presented to you in different ways. So this particular question, you can see that actually they didn't really exactly ask you to find whether is it the equation of the tangent or is it the equation of the normal, right? They just ask you to find the value of P, okay? But by providing you with the various hint and clue in this question, okay? And of course, we need to then make use of the application of differentiation to equation of tangent and normal to help us to solve that. Okay, so let's see how we can actually apply this to this particular question. Now, I know the curve is given here. So I say that the normal to this curve. Now, you notice that they didn't mention exactly at which point, right? But then they said that this curve crosses the y-axis. Actually, it's indirectly telling you the coordinate of the point. Okay, so for this, let us find the dy dx, okay, of this expression. So if I were to write down the dy dx of this expression, so applying the rules of differentiation of for trigonometry that we went through just now earlier on, okay, I'm sure everyone should be very familiar with how to differentiate this, right? So differentiation of cosine will give you negative sign. Okay, but remember inside is a 2x, right? So do not forget your -2 outside. Okay, so you have sine 2x. Okay, and then in this case, differentiation of sine will be just simply cosine. So I will have negative 3 cosine x. Okay, now I need to know what is the coordinate at which point for which the line, the curve crosses the y-axis. Okay, for that actually we can find quite easily, because when it crosses the y-axis, it means that your x must be equal to 0. Okay, so when x equal to 0, okay, I can actually find what is my y. Okay, because I substitute x equal to 0 into my equation for y, I will know what is the y value. Okay, so in this case here, my y will be equal to cosine 0 is actually 1. Maybe I just write it down for you. Okay, 2 times 0, and then I have 3 sine 0, right? So for this, you will get 1. Okay, because cosine 0 is 1, right? Sine 0 is 0. Now, I will also be able to know what is my gradient at this point. Okay, the gradient of the tangent. So in this case here, I substitute my x equal to 0 into my dy dx. Okay, in this case, what I will get is negative 2 sine 0 minus 3 cosine 0. Okay, so for this, we will have negative 3. Okay, negative 3. Okay, once I get negative 3, okay, I will want to know what is the equation of my normal, because the question says that normal to this curve, okay, where it crosses your y-axis, will actually pass through this point. So meaning to say my normal will pass through this point. Okay, so I will want to know what is the equation of my normal. Okay, so with that, I can actually find my normal equation of normal. So this is where we make use of equation of normal here. So okay, that's easy because I know my point already. So one easy way to find equation of straight line. Okay, if you recall this method, okay, either you can use your y equal to mx plus c, okay, or you can actually use y minus y1 is equal to mx minus x1. Okay, you can use either method. So in this case here, y minus 1, okay, is equal to, now this is equation of, this is the gradient of my tangent, right? So remember, in the case of normal, it will be minus 1 over n. So in this case here, this will be 1/3. Right? Equation of my, the gradient of my normal will be 1/3. Okay. And then my x minus x1. So in this case here, my x is 0, so I minus 0. Okay. So from here, I can straight away get my equation of my normal. Okay, which is y is equal to 1/3 x plus 1. Okay, so that will be equation of my normal. So given that this normal will pass through this point, so this means what? When it passes through this point, it tells me that this point will satisfy the equation of my normal. Okay, when a line passes through that particular point, it means that this point will satisfy the equation of that equation of that line. So meaning to say, I can substitute this point into this equation. Okay, otherwise you cannot substitute in, okay, because it will not satisfy that equation. But given the fact that it passes through, okay, so I can now safely substitute this point. Okay, so at this point, p comma 7, okay, I substitute into my equation of my normal, I will get y is 7, 1/3 times x. So my x in this case is my p, right? So I put p and then plus 1. Okay, so once you get to this part here, I think it's very clear already, right? Exactly what is the value for p. So I can easily find that. Okay, so my 1/3 p will be equal to 6. So therefore, my value for p will have to be 18. Okay, so this is how we should actually attempt this question. Okay. Hope everyone is clear with this. All right. Now let's move on to the, if no further question, no other question on this, okay, all are clear, I move on to the next section, okay. Another very common type of application question that they like to test you on, which is on rate of change. Okay, and I know for rate of change, a number of students actually don't really like this type of question, okay, because they find it a bit confusing and doesn't really find it a little bit tough. So for the rate of change, you always have to make use of the chain rule, okay, to help you to solve. And you have to be quite clear exactly which of the information that is given to you, whether are they representing the rate of change of your y or is it rate of change of your x. Okay. Now let's go through this rate of change, okay, in the next question to show you how we apply that. Okay. Now, whenever there is a question on rate of change, I just want to highlight that when there's a change with respect to time, okay, you must be always look out for whether what is that particular variable that is actually changing with respect to time, okay, whether is it the y or is it the x value, okay, and we will write it as your dy dt or dx dt. And if the rate of change is positive, that means your, for example, let's say your x is changing positively with time, that means your dx dt will be a positive value, okay? And otherwise, if it's decreasing, then your dx dt will be negative. Okay, so always look out for that because sometimes they may just give you a certain value, and then you need to look out for whether is it going to be a negative value or is it a positive value. All right. So let me use the next question here to actually illustrate this to show how we actually apply this application to question on rate of change. Okay. Now, for this question here, so this is a cone-shaped cup, inverted, okay, upright. So given to us is that the height is 8 cm. The radius of the circular opening is actually 4 cm. So water is being poured into a cup at a constant rate, okay, which is 5 cm cubed per second. Okay, so you can see this question here. First part, they ask you to show that the volume is given by this expression. And then for part B, they ask you for, at the instant when, let's say, the volume is of a certain value, right? In this case, 18 pi cm cubed. So find the rate of change of the height of the water. And the next part is about the rate of change of the surface area of the water. Okay. So for this question, this is a very typical type of rate of change question, where they would always like to ask you to find what is the rate of change of some of the variable here. Now, reading from this question here, even before we start to do anything, okay, as you read through the question, you need to be mindful of that this constant rate of 5 cm cubed per second, in a way, already tell me what is my value for dV dt, right? Because this is the volume per second. So actually it's the rate of change of my volume, right? So this one is already telling me about my dV dt. I already know that. Okay. Now let's take a look at the first part. Let's do the part A first. Okay. Now, which is to show that the volume of the water level can be expressed as this expression here. Okay. Now, often in rate of change question, you do need to also make use of what you learned previously in similar figure. Okay. So similar figure, sometimes they can actually combine together with your rate of change. But you need to make use of that. So like in this case here, if it helps you, you can actually do your own sketching. You can actually sketch to help you to better visualize. So like in this case here, this is the inverted cone shape, right? So we all know what's a cone shape. So if I look at from the side view of a cone, right, it will be a triangle. Okay. So if I look at the side view of my cup, okay, it will be a triangle. But it's an inverted one, right? Inverted upright. Okay. So the total height is actually 8 cm and the radius is 4. So at any point in time, my water level, let's say in general, right? In general, my water level may be somewhere here. Okay. And this will be representing my height of my water. Okay. So let's say at this point, at this level, let's say my radius is R. Okay, it's R. And then maybe the height of the water is H. Okay, it's H. Okay. So if I were to extend this out, okay, the entire height here is actually 8 cm, whereas this radius is 4. Okay, so can you see that actually we already have a similar triangle here, correct? So I'm going to make use of this similar triangle to help me to form a relationship between the two variables, which is my R and my H. Okay, so from here, if I were to do that, I can actually, using the concept of similar triangle here, okay, my R over 4 is the same as H over 8. Okay, so with that, I will be able to find a relationship between my R and H. So that means I know that my R in this case here will be actually H over 2. Okay, H over 2. Now, why I want to do that? Okay, because in equation that I want to form, I notice that I only have V, volume V, versus the variable H. Okay, there is no R that is present in this equation. Okay, so therefore, this relationship between the two variables R and H will become very useful. Okay, so that I can simplify it to only just one variable. So every one of us will know that to be very familiar, to find the volume of my cone, it will be 1/3 I R square H. Okay. Okay, but now because I know my R is equal to H over 2, so I can replace my R with H. So this will be H over 2 square energy H. So with that, okay, I can simplify to 1 over 12 I H cubed. Okay, so I've shown part A. Okay, so this is the volume of my water. Okay, so at any level, okay, at any level, okay, it can be represented by this equation. So I can use that to solve for my part B. So at the instant when the volume of the water is 18 pi cm cubed, I want to know what is the rate of change of my height of the water. So that means this question here, first part, okay, is to find the rate of change of the water, meaning to say I want to know what is the dH dt. Okay, the question actually asking me for dH dt. Am I right? Because the rate of change of height, okay, which is my H, right? So actually I'm trying to find what is my dH dt. Okay, so let us make use of information that we have to help us to find. So I want to know the value for dH dt, not at any point, at the point whereby the volume is 18 pi. So therefore, we must always find when the volume is at 18 pi, what are some of the corresponding information that we can gather from there. Okay, so let me first write this down. Okay, let's look at B part 1. Let me write here. Okay, so I want to know at the instant when the volume is 18 pi, okay? 18 pi. Okay, now what will be the value for H? Okay, I can find, right? Because I know my volume is actually 1 over 12 pi H cubed. And this is equal to 18 pi. Okay, so with that, I will be able to know what is my H cubed, right? So I can simplify that. Pi and pi can cancel away. So this one will give you 216 if you use a calculator. So from here, I know my height is actually 6. Okay. Now this H equal to 6 is important information, right? Because it tells me that it's when the height is 6, then the volume will be 18 pi. Okay, so when it's 18 pi, it corresponds to the height to be equal to 6 cm. Okay, so with that, since I know the expression for volume of V in terms of H, I can also know what is my dV dH. Okay, dV dH. Okay, if I differentiate my dV dH, okay, because my V is this, right? Okay, this is my V. Okay, this is my V, huh? Okay, this is my V. So dV dH will be just simply, okay, you bring down this power, right? So this will become 3 over 12, which is pi over 4. Okay, and then the H cube, you will reduce this power by 1. Okay, 3 minus 1, right? As what just now we went through by teacher Quilin. So with that, I will have pi H square over 4. Okay, so that's my dV dH. Okay, now let me do the next part. Now, since I know my dV dH, okay, I will be able to also know the value of my dV dH. Okay, because I found that when the volume is 18 pi, I know that my H is actually 6. So from here, I actually know that I know my value for dV dH. Okay, so now let's take a look at the chain rule that I'm now trying to form. Okay, that will help me to find my dH dt. Okay, so what is the chain rule here? Okay, now you have the, okay, let me write this. Okay, my dV dt, okay, will be equal to dV dH multiplied by dH dt, dH dt. Okay, this is my chain rule, right? Okay, so bear in mind, I want to know what is my dH dt. But do I know what's my dV dt? Yes, I know, right? Because from the beginning of the question, can you see my dV dt is actually this 5 cm cube, right? Okay. So water is being poured into the cup at this constant rate. So that means my volume is increasing, right? It's increasing. So therefore, I know my this dV dt is a positive value. So this is 5. Okay. And do I know my dV dH? Yes, I know, right? From the earlier part here, as I mentioned, because I can know what's the value of dV dH when it corresponds to the height of 6. So from here, I can substitute this value. So this is pi H. I will put down as 6. Okay. Then over 4. Okay. And then multiply by dH dt. Okay. So from here, I will be able to know what is my dH dt. dH dt. Okay. So you can just simply solve for this. You'll be able to find that my dH dt will give you 5 and 9 pi, okay, centimeter per second. Okay, so this is how I can actually apply the chain rule here to find what is my dH dt. So as you work through the question, always be very mindful based on the information that they gave us, whether this information represents dV dt or is it dH dt or what, you know. So in this case here, since it's volume, so I know my dV dt. Okay, now I need to know what is my dV dH. Okay, when that corresponds to a height of 6, okay, because my H equal to 6 come from the volume when it's 18 pi. Okay, so I need to satisfy that. So that's why I need to know at the instant when it's 18 pi, right? So I need to know what is the corresponding value for H, because all my variables are all in terms of H. Okay, so therefore I want to find that. Okay, so that's the reason why I want to know what is the H value when my volume is 18 pi. Okay, so I'm explaining this to you so that every one of you, as you do, you understand exactly each of the steps. Okay, and actually why are we doing that calculation? Okay, so for a certain reason, we calculate to find that value is for a certain reason and purpose. Okay, so that's how we do part B part 1. So let's take a look at B part 2, okay? B part 2. So B part 2 is to find the rate of change of the surface area of the water in the cup. So again, the rate of change of the surface area at which point? Okay, it's also based on when the volume is 18 pi. So when the volume is 18 pi, it also means that the height will be equal to 6. Okay, so now I'm going to find what will be the rate of change for the case of my area. So let's find my expression for my area. So for area, in this case, I know it's pi r squared, right? So pi r squared, okay? But I know my expression for r is what? H over 2, okay? So again, I'm going to write everything in terms of variable h. So this is h over 2 squared. So once I got that, okay, I will know that my area is just simply pi h squared over 4. Okay, so once I got that, so I can find what is my dA, my rate of change of area with respect to h, okay, dA dH. So differentiation, this is a simple differentiation, so it will give me 2 over 4, which is half, so pi h. Okay, now once I got this same thing, I will have to write down my chain rule. Okay, so chain rule, okay, just now was dV dt, right? Now it will be dA dt. Okay, and then I have my, instead of dV dH, I have dA dH multiplied by dH dt. Okay, so this is my chain rule involving the area. Okay, so far? Okay, so once I got that, then same thing. Okay, I want to know at the instant when your volume is 18 pi, which means my H is equal to 6. Okay, so let's see what do we know here. Okay, now I want to know, in this case here, my dA dt. So let's see, do we know my dA dH and my dH dt? Yes, I will know, right? Because my dA dH, which is in terms of H, is actually half pi H. Okay, but I want to find, in this case here, at the instant where the volume 18 pi, my H is actually 6. So I put a 6 inside. Then I multiply by my dH dt. My dH dt, actually, I know for my B part 1, okay? Because dH dt was found early on, right? This one, this value, 5 and 9 over pi. So in this case here, I can write it down, 9 over, 5 over 9 pi, sorry, okay, 5 over 9 pi. So I just multiply this together. That will give me, okay, pi and pi can cancel away. So in this case here, you should get 1 and 2/3. Okay, 1 and 2/3. So be careful with your unit. In this case here will be centimeters squared per second. Okay, so this will be my dA dt, the rate of change of my area, or my surface area. Okay, at the point whereby the volume is 18 pi. Okay, so this is how we should solve this this question, right? In applying your differentiation to rate of change for this type of question. Okay, so the question for this type of rate of change is very what I want to highlight to you is more in terms of the method. Okay, so they can change the question. It can be volume of a cone, it can be a sphere, it can be any other object, okay, or any other context. Okay, but the approach is always the same. Okay, first, usually they give you an object or any kind of object, whereby you may end up having two variables. So you must always try to express one of the variable in terms of the other variable. Okay, so that your final expression will only have based on one variable, okay, not two variables. Like in this case here, right? If I based on originally, that means I got 1/3 pi r square h, right? That means I got r and I also got I have a h. So it doesn't work, right? You must only have one variable. Okay. So therefore, there's always a step where I need to do to try to form a relationship. Okay. So using similar figure is something that you should look out for. Okay. Where possible, you must look out for whether is there any situation whereby you can use similar figure to help you to solve to find that relationship. Okay, then the technique will be just finding out what is your rate of change of the variable that the question is asking you. Like in this case here, you're asking for the surface area as fine as the height. Okay. Okay, so that's for rate of change. Now moving on to the next type of question, your stationary point, your maximum, minimum kind of problem sum. Okay, for this type of question, I would say that it should not be difficult question. Okay, but nonetheless, I hope everyone should learn this well, because the technique to find this kind of, to solve this kind of question is pretty standard, I must say. Okay, so there will always be to find what is your stationary value. And your stationary value will always be determined by your first derivative test. Okay, and you will always equate your dy dx to be equal to 0, right, to find your stationary point. Okay, now I've asked some students, and there are some students who just simply remember the step. Okay, first find your first derivative, then after that use a second derivative to determine whether is it a maximum, minimum, and after that, you are more or less done and solve the question. Okay, but then there are the students who actually they don't really understand why it's like that. You just follow the step. Dy dx equals 0, and then after that you find the stationary point. Now, why is it that is your dy dx must be equal to 0? Okay, so please appreciate that as well. So if you have a curve, right? You have a curve. Now you have a curve. A curve can be any shape. Okay. Now your gradient at any point is represented by your dy dx. So if you have any point here, for example, a point here, or let's say a point here, right? You will have your dy dx that is sloping in a certain angle, right? In a certain slope. But you will find that only when you are at the turning point, then your gradient will be flat. Okay, will be flat. Okay, will be flat. Okay, only at the turning point. Okay, so when you have this kind of situation, then this turning point can be either a maximum turning point or it can be a minimum turning point. Okay, so that's the reason why every time when we want to find the stationary point, okay, so the word stationary means that actually the gradient is actually 0. Okay, that's why it's called stationary. So therefore, that's the reason why we must always find dy dx equivalent to equal to 0 to find what is that turning point. Okay, and whether that turning point is it going to be a maximum point or minimum point, then that's where we can use either the second derivative test to help us to solve, or we can actually also use the first derivative test. Okay, so the first derivative test is what I've shown here in this table. Okay, which is a very typical method, which I'm sure many of you will actually have learned the same approach as well, right? You just simply take a value that's slightly smaller and a value that's slightly bigger, and you determine whether the gradient is negatively sloped or positively sloped. And then you can determine in this whether is it a maximum point or minimum point. Okay, now, most of the time, always try to use your second derivative test, okay? Because it's a lot more easier and neater, okay? And I know most people like to use second derivative test. Now, do you all know when do you need to then use the first derivative test? Okay, anyone? Now, there are some situations whereby you need to use the first derivative test. Okay, let me just pose this question to all of you. Anyone can tell me, in what situation do you then need to use the first derivative test? Okay, good. I had some response. Any more besides the response? Okay, what I see is that some of you mentioned that yeah, dy dx equals 0, right? So your dy dx equals 0. It's not negative, it's not positive, then what? Okay, yeah, so some of you mentioned point of inflection. Yes, okay. So that is one reason, okay, one reason whereby you have to use the first derivative test. Okay, when basically it's not conclusive, huh? Okay. Now, how about another reason? Is there another reason? Anyone? Anyone able to tell me a second reason? Okay. Now, a second reason as to whereby we also use the first derivative instead is when sometimes the differentiation of my second derivative is very difficult or very tedious. Okay, so you may have a function that whereby you differentiate a second time is going to be very complicated. Okay, whether you have to use a quotient rule that's going to make the whole thing very complicated. Okay, so in those situations, we will also can use the first derivative test. In that kind of situation, you'll find that the first derivative test can be an easier method. Okay, because you don't need to bother about the very complicated differentiation because of the function involved. Okay, you don't need to just substitute a small value that's slightly smaller and a value that's slightly bigger, and that's it. You just need to determine the sign, whether it's positive, negative, and that's it. Okay, so that is another occasion whereby you may find that using the first derivative test to be helpful. Okay, so these are the typically the two type of situation. Okay, but yeah, usually in O level you won't get too complicated a second derivative. But for some of you who are aspiring to go into to do your A levels, you will then have a lot of opportunity whereby you will encounter a lot more complex function, whereby the differential can be a bit tedious. Okay, so then you will have that kind of opportunity to find the first derivative test to be very helpful. Okay, so that is a quick recap on this part here. So let's look at the question here and to see how we actually apply this. Okay, so for question number 7, we have this information given to us. Okay, we got this piece of wire, 150 cm long, bend into this shape, and then you're given some information here. And part A, express y in terms of x and pi. Okay, so let's do step by step. So a lot of times, all this question here is in a way guided. So long as you do the step accordingly, in a way, it's actually to help you to get the final result subsequently. Okay, so let's do the part A first. Okay, this is not a difficult shape. Okay, so express y in terms of x and pi. Okay, so in this case here, okay, okay, you can refer to your diagram, okay, because I can't show the whole diagram on my screen. I need to use the space here. So you refer to your diagram. So from the diagram, you can see that to find the parameter, I can use the parameter to help me to form the relationship, right? Since I know the total length is 150. So in this case here, I have a 2, 5x, okay. And then I also have y, right? Okay, I got 2y, right? Both sides, okay, 2y. And then I have that semicircle. So my pi d, right? Pi d. So pi times the diameter, which is 4x. Okay. Okay. No, 8x, okay. But then I will be because it's a semicircle, right? So I must times half. So actually it's therefore 4x. Okay, so I should be pi times 8x and times the half, right? But I can simplify it to just simply 4x. Okay, and this thing must be equal to 150. Okay, because that's the whole entire length. So with that, I can actually simplify. Okay, I can simplify this. So my 2y will be equal to my 150. Bring over all the other term, all the x term. So 4 pi x. Okay, and from here I can then simplify. So this will be 75, right? I divide everything by 2. So I have 5x, and then here will be 2 pi x. Okay, so part A easily solved, right? So let's take a look at the part B. Okay, part B. Now, part B is to show that the area is given by this expression here. Okay, so again, it's not too difficult. Okay, so we can also find the area. Right, so for area, okay, let's put A equal to, okay, so I've got a triangle, so half based on height. So half base is 8x, 3x, okay. Okay, why I say 3x? Okay, because if you notice, this is 5x, this 8x, so half of this will be a right angle, so this must be 4x, right? So I think by now you should have done a lot of Pythagoras already, right? You all should recognize the figure, right? 3, 4, 5, right? If this is 5, this is 4, here must be 3. Okay. Okay, using your Pythagoras. Okay, if you are not, you cannot recognize the number here, it is a very nice number for Pythagoras. You can always use your Pythagoras to find, right? So 25 squared, minus 16 squared, and then you will get 9 squared. So square root, then you get 3, right? So that's why I know here is 3x, okay? So with that, okay, I have my area of triangle, then I plus the other area. So 8x, okay, times my y, okay, this is my rectangle. But then from the first part, I know my y, because I want everything in terms of x. So instead of writing y, I will write 75 minus 5x, 2 pi x. Okay, and then I plus the semicircle. So pi r squared. Okay, pi r squared. So again, you can just simplify this whole thing. Okay, so if you do it carefully, you should be able to simplify this, become 12x squared. This will become, I got 600x. Okay, 40x squared. 16 pi. And 8. This will be 8 pi x squared. Okay, so you can simplify everything. Okay, so you should be able to get 600. Okay, so I just factorize out my x squared. So they will become 28 and your 8 pi. Okay, so from here I can simplify to 600x. Okay, factorize out the 4. So I have 7 plus 2 pi. Okay, and this is what they want us to show, right? So I got part B. Okay, now let's move on to look at my part C. So find the value for x for which x has a stationary value. Okay, so for stationary value, okay, everyone should be very familiar, right? We always find what is my dy dx. Okay, so in this case here, my is in terms of a, so it will be my dA dx. Okay, dA dx will be give you 600. Okay, so I simplify this. So this will be 7 plus 2 pi. Okay, this is just a constant, no change. So this become x, right? So once I got that, then I will know that I can equate my dA dx to be equal to 0. Okay, to find the stationary point. So with that, I will be able to know 600 minus 8, 7 plus 2 pi x is equal to 0. So with that, I can find what is my x. Okay, if you can solve for this, you should find that is 600 over 8 and then 7 plus 2 pi. Okay, so this is my x. So if I were to use a calculator and simplify, you should get 5.65. Okay, based on 3 assets. All right. So that is my stationary value. So let's look at part B. So they find the value of A. Okay. So what's the value for A? Stationary value for A. So for part 2, since I know x is equal to 5.65, I can find the stationary value at A. Okay, at A. So that will give me, just substitute x into the equation. Okay. So whenever you do this, right, always remember this is the rounded off figure. So please do not use 5.65, okay? So when substitute the value, you must try to use the more exact value. So I'm going to use the value that is before I round off to 3SF. So for my calculator, actually I get 5.6462. Okay. Now you can actually go up to 4 or 5 decimal. That should be quite enough. Okay. So don't need to really go until to 7, 8 decimal. Okay, no need. Okay. So unless want to be kiasu a bit, so you can go to 5 decimal. I think should be enough. Otherwise, 4 is actually quite okay already. So you can based on that, and then I can substitute the other value. Okay, so this will be 4, and this is 7 plus 2 pi. Okay, and then 5.6462. Okay, then you square it. Okay, so with that, then I can find my value. Okay, so in this case here, you should get 1690. Okay, same thing. If I round out to 3SF, 1690 cm squared. Okay, so that's my stationary value. Okay, so part 3, I want to determine whether it is going to be maximum or minimum. Okay, so in this case here, which one would you all like to use? First derivative or second derivative test? Okay, I'm sure many of you all would choose the second derivative test. Okay, so when you differentiate the second time, you find that actually it's not difficult to differentiate, right? It's actually quite easy, right? So the x will be gone. So you have 8, 7 plus 2 pi. All right. So in this case, 7 plus 2 pi is definitely a positive number. I multiply by a negative number, so I know for sure this is going to be less than 0. Okay, so therefore, I will know that my stationary value, okay, stationary value of A, okay, is going to be a maximum. Okay, right. Okay, so this is for this question. Okay, yeah, I think we overrun a bit. Okay, but I will going to stop here. Now, are you okay so far? Anyone has any question that you'd like to ask or clarify? Okay, let me see any question from the chat. Okay, Ken, yeah, some of y'all actually responded to my earlier question. Okay, yeah, very good. Okay, Ken. Okay, now, any question for anyone? Okay, if not, then I will not want to hold you back. Okay, but before you leave, I just want to highlight to you that for differentiation, okay, typically these are the few types of application that you will get to see. Okay, so that's why for tonight's set of the material, actually I've purposely prepared some of the notes, and then for each of the accompanying notes for each of the application types, we have a question, okay, for you to illustrate the application of the concept to the different style of question. Okay, just remember to learn the approach and understand the method. Okay, the question can always change. Okay, but the method doesn't change. Okay, the method that you have learned for each of the application, be it rate of change, be it increasing function and so on. Okay, or maximum, minimum. Okay, the method is always the same. All right. So the function can change, the context of the question can change, but the method remains the same. So just remember that. And of course, the technique of your rules of differentiation, please know that very well. Okay, so at the beginning, okay, actually I summarize for everyone a very concise set of the summary of all the different differentiation rules. Okay, please use that as a quick revision for yourself, a concise revision notes for you to make sure you know them very well, because it will help you not only for differentiation, but it will also help you for your integration as well. Okay, because to do integration, you also need to know the differential very well. Okay, it's going to help you. All right. Okay. Now, if no further question for everyone, okay, I wish you all the best. Okay, in your paper, upcoming paper. Okay, and good luck, everyone. Okay, and if you have any question, you can let me know now. Okay, if not, then okay, I think I will stop here. Okay, all the best, everybody. Okay, guys. Okay, 加油.